Bismillahir Rahmanir Rahim. At the age of 14, I started with the first verse of the Quran. Alhamdulillahi Rabbil Alameen. God alone is worthy of praise, for He is not only the creator, but the sustainer of the universe. So as a 14-year-old, I wondered how I could really believe that. And it's remarkable that I decided that physics is the subject that's going to answer the question, because physics is the study of the physical universe. And if you study the physical universe, surely someday you will find out who the creator of the universe is. And now, almost 45 years later, having worked at the absolute frontier of human knowledge, at some of the most breakthrough experiments that mankind has done, I testify through my intellect that there is no question that Lord God, Allah, is the creator of the universe. And He created the universe. And if you look at the universe, you see billions of galaxies and billions of stars. But that doesn't impress me. But what impresses me as I look at you, God created human intelligence. The whole universe has been tuned to produce intelligent life like ours. And if God has created intelligent life, then it cannot be in vain. So why did He create it? The reason God created the universe and gave us intelligence is to see if we can build, in one sentence, a just universe. And so I believe as a teacher, I'm serving God's purpose because I'm trying to create a better universe. And that's true for all of you. So with that, I would now like to start my presentation. For the last 40 years, my life has been dedicated in a passionate way to discovering what is the ultimate structure of matter. And I have built up a program of experimental particle physics at the University at Albany and set up the Albany High Energy Physics Lab, where in collaboration with major world experiments, I have tried to find what is the structure of the universe. And I'll tell you, we have very limited time, but I decided that I'll give you a glimpse of what this great achievement of Western science is. And along in the backdrop of my research, I decided that I shall devote at least 10% of my academic time to bringing students from third world countries like Pakistan, India. India is no longer a third world country, but Pakistan, India, Nepal, Ceylon, Turkey, and people also from Germany, and trying to put them through a PhD program here at Albany. You'll excuse me, but I have to tell you a little bit about myself. I started with a master's in physics from Dhaka University in Bangladesh and ended up with completing my PhD in 1975 at Indiana University, Bloomington. But my experiment involved working at the Stanford Linear Accelerator Center, which about the time that I graduated made a fantastic discovery. A discovery which finally led to the synthesis of the standard model of particle physics. And I was lucky enough to join the group of the 1976 Nobel Prize winner, Bert Richter. And I guarantee you, if you work with a Nobel Prize winner, it will change your life, it will change your perspective. Every single member of the group is now a full professor and a group leader somewhere. I arrived at University at Albany, where I started my academic career. In '95, I became a professor, and in the last 3 years, I have been the chairman of the department. I have been part of these most famous experiments, the Mach II experiment at SLAC, which is responsible for the discovery of the fourth quark containing the quantum number charm, and also is the scene for the discovery of the third lepton called tau. After that, I arrived at Cornell University in the CLEO experiment, which became a center for the study of charm, beauty, tau. And then I joined in 1995. In 1995, I joined the Atlas experiment, which is probably the most ambitious scientific experiment ever launched by man. The experiment was approved in '95, and in 2007, we'll start taking data. And in the meantime, I have been working on the Babar experiment at the Stanford Linear Accelerator Center, which has already discovered what is called CP violation. CP violation is a complex theoretical idea, but I can explain it in a very simple way. At the beginning of time, when there was nothing and the universe was created, equal amounts of matter and antimatter was created. All the antimatter has disappeared. And that's the billion-dollar question: where has all the antimatter gone? Well, one of the explanations is CP violation. So we have been trying to see if we can detect CP violations in experiments we do in our lab. And this is the second example of CP violation being discovered. And it'll take at least another 20 years before we really understand the results of these experiments. Well, I've been at the University at Albany, which is part of the state of New York university system. This is the largest university system in the world, with about 500,000 students registered at any given time, and has a budget of about $1.2 billion. And the University at Albany has 17,000 students with about 5,000 graduates, has a budget of the order of $500 million, and 600 full-time faculty. My own department started as a big department, but has shrunk to about 13 faculty members. Part of the reason being a group of people broke away from the department and formed what is the first College of Nanoscience and Nanoengineering on the campus, which has grown into a behemoth of almost $3 billion of facility. And so we are left in the physics department pursuing basic science. We have 13 faculty members. We support 40 PhD students, 50 undergraduate students, and something that we are proud of is over the last 30 years or so, we have produced 220 PhDs with an average faculty size of 20. There are people in the department who have produced 50 PhDs over a lifetime. That's something that we are very proud of, and probably one of the highest number of PhDs produced. Even now, with 13 faculty members, we produce between 5 to 10 PhDs per year, 10 to 15 masters, and 10 to 15 BSs. People talk big about all kinds of assessment. For me, if you just give me these three numbers for any department, I can figure out how good the department is. You don't need big fancy studies. If you tell me the number of PhDs you're producing, you essentially tell me how good department you are. Okay, as an experimental physicist, our goal is to understand the structure of matter in terms of the smallest fragments and the forces that hold these fragments together to form the visible and invisible universe. These 2 points were raised by Democritus and Leucippus almost 2,500 years ago. But now we can answer this question with considerable confidence based on experiments. And of course, we would like to understand the role played by matter and force at the beginning of time and the tools and instruments necessary to answer these questions. That's what we build. And finally, what do we do with this? Well, we use the knowledge thus attained for the advancement of human civilization to teach others what we learned from our quest. Most of us are not aware of this, but the search for the structure of matter in the last 100 years has produced tremendous spin-offs, especially in the medical field. When you see an X-ray, when you see digitized subtracted X-rays, when you see ultrasound, when you see MRI, all of these have come out from modern physics lab, where our goal was primarily to understand the structure of matter. And a lot of people have difficulty in understanding. They say, why the hell do you care? Well, the answer is because we are human beings. We have been programmed from the very beginning to seek out and to learn about the world at this level. What can be more intellectual? What could be more exciting than that? Well, let me go back here. You see, most of us know about the atom. The size of the atom is 10 to the minus 10 meters. But we have gone deep into the heart of matter. We have gone into the nucleus, into the proton, and now we are studying matter at the level of quarks, of which protons and neutrons are made. And of course, the electron here also comes. So while you are talking about nanoscience and nanoengineering, which is 10 to the minus 9 meters, we are working at 10 to the minus 18 meters. So we are doing attoscience. One of the sort of major surprises is in the last 15 to 20 years, we have discovered that we only know less than 10% of the universe. That only 10% of the universe is hot and luminous, so we can see them through our telescopes. But 90% of the universe is cold and is dark. So we really don't know what they are. But talking about the visible universe, we really have a synthesis. We can divide the visible universe into matter and energy. Matter can be broadly divided into leptons and hadrons. Hadrons are like protons and neutrons. They experience the strong force. Leptons are like electrons and positrons. They do not see the strong force. And then hadrons themselves fall into mesons and baryons. And when I was a graduate student, we didn't know why matter, the hadron, broke into mesons and baryons. But since then, we can give you a very reliable answer on that question. As far as energy is concerned, energy is brought about by the forces, and the force is brought about by the exchange of force carriers. There are 4 different forces. The electromagnetic force is mediated by the photon. The Z0, W plus and minus, they mediate the weak force. The G is graviton, which mediates the gravity, and G is gluons, which mediates the strong force. So we thought that there are just a few mesons, but then we discovered how to build accelerators, accelerate electrons, protons, and bombard them on targets like hydrogen, deuterium, beryllium, tungsten. And when we did that, we suddenly had chaos. Over the next 30 to 50 years, between 1940 to 1970, we kept discovering particles after particles. These are subnuclear particles. And it's almost like we had a zoo. And in a zoo, you know, you have all kinds of animals. So these are all kinds of animals. But as we discovered them, as we cataloged them, we found that we could begin to see some order. For example, mesons seemed to have spin quantum numbers of 0, 1, 0, 1, 2, and they all came as a spin multiplet, and the members of the multiplet were like 9 in each case. And then they split into some other categories in each of these multiplets. We found that in order to understand them, we had to invent another new kind of charge for matter. We gave it the name strangeness because it appeared weird to us at that time. And the name strangeness has stuck. In the same way, if you go to baryons, like protons and neutrons, there's also hundreds of them. Okay? And unlike the mesons, they fall into groups of octet, decuplet. And instead of spins of 1, 2, 3, they have spins of half, 3 half, 5 half, different versions of 5 halves and 3 halves. So as far as when I was a graduate student in the early 70s, the state of particle physics was a state of biology. A lot of flora and fauna, a lot of mesons and baryons. They didn't make sense. And you were almost at the level that particle physics appeared boring. So how many of these resonances are you going to discover? But then, you know, we were able to make a synthesis. In 1964, Gell-Mann and Zweig predicted that these particles are not elementary particles. That was what we thought, that these particles, since there's so many of them, they are bound states of smaller particles, which were given the name quarks. Quark is just a funny word, you know. The author Gell-Mann was reading a book which had a funny statement, 3 quarks for Mr. Mark, just a funny comedy statement. So he said, why not call them quarks? And so the name quarks has sort of stuck. And what we now can explain is all of the mesons that are bound states of quarks and antiquarks. And unbelievably, only quarks and antiquarks form bound states and appear as mesons. There are no bound states of 2 quarks. And again, for baryons, they are bound states of 3 quarks. As you see over here, there are bound states of 3 quarks, or there are bound states of 3 antiquarks. And all other combinations do not exist. This is still somewhat of a mystery which we are trying to understand. What is so special about the quarks that only special combinations exist in nature? So finally, I'll tell you the answer to the 2,500-year question that Leucippus and Democritus asked. What is the world made of? What is it that holds it together? Well, I'll tell you, the world is made up of two kinds of matter. The world is made up of fermions, which have half-odd spins. And the world is made out of bosons, which have spin 0, 1, 2. The mass of the universe comes from the fermions. Fermions fall into 2 categories, leptons and quarks. Quarks have this special property that they see a strong force. And in order to explain that, we had to introduce a new property for quarks, a property that can take 3 values. This property we call color because we have 3 primary colors. But it has nothing to do with real color. So we say that there are 6 quarks, and each quark comes in 3 colors. So there are 18 quarks. And then Dirac had shown much earlier that there is another symmetry in the universe. For every particle, there is an antiparticle. So for an electron, you have a positron with the opposite charge. For a proton, you have an antiproton with the opposite charge. And of course, all of matter is made out of particles and not antiparticles. But we can produce antiparticles in our lab. So total of 36 quarks. And then we had 6 leptons and 6 antileptons. So the whole universe, everything, this table, U, we are all made out of total of 12 leptons, 36 quarks. So there is a total of 48 elementary particles. And when I say elementary, that is the best word I can use. As an experimentalist, all I can say is if these particles do have size, the size is less than 10 to the minus 18 meters. That is what we can experimentally resolve. And not only that, we are able to explain that mesons are quark and antiquark. And for example, the proton is made out of 2 UUD quarks. The neutron is made of UDD quarks. Now, before 1974, all the known particles could be explained by assuming there were only 3 quarks, up, down, and strange. And then in 1974, when I was a graduate student, a fantastic series of discoveries happened at the Stanford Linear Accelerator Center. A new series of particles were discovered, and the only way you could explain it is to posit that there is a fourth quark, the charm quark. Before this, nobody believed in quarks. Even the guy, Gell-Mann, thought that quarks was just a theoretical idea. But the discovery at SLAC changed all that. And I arrived as a postdoctoral fellow in 1975 at SLAC. It's probably one of the most exciting times in particle physics. Every day, I didn't have to think what to do. We were searching for particles. And my career of discovering particles started at Stanford. I started discovering at the rate of about 1 particle every year. And the search goes on, and even this year we have reported a new particle. For what it is worth, the idea is to discover all the particles that are predicted by this model. And the model, I'll show you in a minute, would predict an exact number of particles. So if you find all of them, then you have made a tremendous advance. And if you don't find one of them, that means your model collapses. So then you have to start all over again. So it turns out before 1974, there were only 3 quarks. So if I look only at the baryons, then you get 3 into 3 into 3, 27 combinations. So there should be about 27 particles corresponding to that. But it turns out that if you break it according to their symmetry properties, they break into groups of 10 and 8 and 8 plus 1. The 8 and 8, they have a common mixed symmetry. So what happens is these 2 particles, they mix, and you only see 8 of them. So you're going to see, and the singlet, there are explanations why it may not exist. So you should see a decuplet of particles, and you should see an octet of particles. All of these had been discovered already by the time I was a graduate student. But then when the charm comes in, the action gets hot. Suddenly, using the model that explains all of them, any graduate student would be able to predict what new particles will be formed. Suddenly, instead of 10 and 8, we'll become 20 and 20. A total of 22 new particles containing the charm quark will be found. And if you notice, the second level contains 1 charm quark, and this level contains 2 charm quarks. This one contains 3 charm quarks. Now, below this level, we have seen everything. And my life for the last 30 years has been spent in mapping this. 3 minutes? Okay. Well, I'm going to speed up. And all these pink particles have been reported by me for the first time. So, this is what a particle detector looks like. 600 people spent 10 years of their life building it. And then for the next 10 years, we stake data. The data are data of collisions like that. This is the picture of the Atlas detector. And if you look at the size of the human being, this is a monster. This will come into existence in the next 1 year. The other thing that I do is I learned how to make cheap supercomputers because I need so much computing. By connecting PCs, I can make a supercomputer and beat IBM by a factor of 20. So in my group, our graduate students, we build supercomputers. A supercomputer is a device that can do 1 billion floating point operations per second. This is called a gigaflop. This machine can do 25 gigaflops, and it was put together by graduate students and undergraduate students. So this is sort of the main thing. I have, in the last 20 years, supervised about 20 students. 15 of them have completed their PhD. Another 5 are in the process of completing their PhD. And the PhDs are all discoveries. It's either a high precision measurement, the discovery of a new particle, or the discovery of a new decay of a particle. So in blues, I have shown you that. Started in 1989 with my first graduate students. I have reported the discovery of more than a dozen new charm baryons, and supervised about 20 students at the PhD level, half a dozen at the master's level, and 1,000 at the undergraduate level. And I'm proud to say that the first 3 Pakistani women to complete their PhD in experimental particle physics did that in 2006. 2 of them, Samia Zain and Shamona Ahmed, are my students. Here's a picture of Samia Zain receiving her PhD in May 2006. She's a very smart woman, and she did her PhD with one 8-year-old, and in the last year of her PhD, she got pregnant and came to work till the day of her delivery and was back 6 weeks later. So it's really impressive. I mean, there are 2 women, both of them completed their PhD. She completed her PhD in record time of 5 years. She's a very smart woman. She was so smart, I decided she's going to be my postdoctoral fellow. So she's still working in my lab. So over the last 20 years, I have recruited about 18 students from Pakistan, Bangladesh, Ceylon, and about 11 of them have done their PhD, and they're all gainfully employed. About 5 of them have gone back to Pakistan to work there. Also set a program of visiting scientists. Several of them, even senior scientists, have visited my lab. And I'm going to close with this idea that I would like to form a scholarship foundation. The concept is to fund Pakistani students for PhD in US from funds given by local Pakistani expatriates. They all ask the question, what can we do for our country? Well, all I ask them to do is to pay me $150 per year. 150 into 100 families gives me $15,000. The university has agreed to waive the tuition. So it costs about $25,000 per student, but with the tuition gone, it's only $15,000. And I presented this idea at a meeting of Pakistanis in New York, and several people walked up to me with their checkbooks. So I'm getting set up for this, and I believe that if properly organized, we could bring 100 people for PhDs in US every year. And I mean, since I'm not in Pakistan, I'm too busy with my research, I still would like to contribute, and you can contribute at a big level or at a little level. And there are 2 other Pakistanis like me. They are also bringing students. Between the 3 of us, in the next 5 to 10 years, we will produce almost 50 to 60 PhDs in physics. That may be more than all the PhDs produced in Pakistan in the last 10 years. So the point is, we can't, I've also set up a scholar exchange program. And finally, my answer is, can one person make a difference? The answer is yes, if one is motivated to help. I spend about 10% of my academic time in recruiting students from Pakistan. Students recruited may work with any professor, so that's a good thing. Other professors are also happy. So when I put up a Pakistani student for a TA position, they do not consider that they are doing me a favor. They think that the students who come will also work for them. And I visit Pakistan, I visited Bangladesh, and I give talks, and I try to recruit the best students from there. Most of the students I recruit are in the top 10%. And not one student has failed to pass our comprehensive exam. So I really believe that instead of talking big, I'm an experimentalist, I do an experiment. This is an experiment I've done, which I think has been successful. Everybody in the Pakistan academic community knows that I am always willing to help students. And while I'm a little biased towards Pakistan, I am willing to help anybody from any third world country. And even from first world country, I have a lot of students. I have 3 students from Germany who have done their PhD with me and about 3 masters with me. I'm committed to pushing the frontier of human education. That has been, for the last 30 years, the goal of my life. And it has been very satisfying. And I do it not for any personal gain. This is my taqwa. This is how I can stand before God and say, indeed, I have tried to create a just world. Thank you very much.